Hello everyone, welcome to this training that was designed for the Copernicus Marine Service Marine Workshop Marine Data for Africa. My name is Alexandre from Noveltis and I will be your trainer for this session. So in this training we'll be studying the Congo reverse discharge in the Atlantic Ocean. So here's a brief overview of the region that we will be studying. So the Congo River is one of the most important rivers in Africa. It's one of the longest. It's one of the widest basins. It also has one of the biggest discharges in the Atlantic Ocean. So monitoring what happens at the mouth of this river is quite crucial. In many ways, so to understand how nutrients are discharged in the ocean, but also polluting products, for example. In the case of pollution, it can help pinpoint pollution hotspots in the area, and perhaps help make decisions in terms of policies regarding economic activities based on land or also industrial activities. So in this training we'll be using a few products that are available on the Copernicus Marine Service catalog in order to visualize phenomena that can happen in this region. And so in this training you'll learn how to open and manipulate these products and to visualize data based on this case study. So here is a brief overview of the data that we're going to use. So first of all, we're going to study three main variables. So sea surface temperature and salinity, which are highly affected by river discharge. Because of course, for example, salinity tends to decrease, of course, at the river mouth because the river discharges a lot of fresh water. And we'll also be studying chlorophyll because chlorophyll is sensitive to the amount of nutrients that is carried by the river from the land. And chlorophyll is also a good indicator of the presence of phytoplankton, because the phytoplankton use chlorophyll to carry out photosynthesis. And phytoplankton is a good indicator of the presence of marine wildlife that is attracted to it, which is why chlorophyll is, in the end, a good indicator for the presence of marine wildlife. So here is the complete overview of the studied region. So we are at the center. There is the map of the Congo River. So you can see the coordinates of the box we're studying. We will be studying the deep ocean at a level of depth from 0 to 100 meters. And we'll be studying over a period of time of about 2 months, so from February 2020 to April 2020. So to go in more detail about the products, so for temperature and salinity, we'll use a model product, which is this one, Global Analysis and Forecast for Physical Variables. So here you have a brief summary of its spatial resolution and its temporal resolution. So if you want to know more about the products, you can always take a look at the user manual of the product by clicking those links. So here's an example. So we're using a similar model for the chlorophyll, except here is dedicated to the biological variables. So it's also a model product. So same thing here. You can always check out the dedicated documentation in order to know more about the products. And those model products will be compared to observation products. So those are derived from satellite observation. So we'll use the ocean color observation to derive the chlorophyll variable. and we will use this SST product, also based on satellite observation, to have our sea surface temperatures observation products. So the data that is necessary to perform this training is already provided. However, here's a brief section about how to download data using the new Copernicus Marine Toolbox API designed for Python. So the Copernicus Marine Service has developed this library that is available when you perform this training. If you select this kernel, make sure when you start the training to select this CMEMS version 4 Python kernel. Otherwise, the new library may not be available. And so this allows you to directly research and download the desired products from the Copernicus Marine Service without having to visit the Copernicus website. So it's quite simple. You just import this library and then use a subset function. And there are several arguments that you need to specify in this function. So first of all, you can retrieve from the Copernicus Marine Service website the ID of the dataset that you are choosing. For example, here, in this example, we're retrieving the sea surface temperature observations that I've talked to you about before. Here you select the variables that you want to retrieve. So here we only want the sea surface temperature. And here you retrieve the date range that you want to study. And finally, you specify here your longitude and latitude boxes to specify your area of interest. And finally, you decide in which directory you want to download your data. So here we specify the data directory, so which is here. This is our notebook, and this is the data directory. So when you execute this function, so the API will ask you for your Copernicus Marine Service credentials. So I'm going to quickly demonstrate how it works. So apparently, you can see that it found the product that we have specified. It gives you an information about the estimated size of the product that you're downloading, and by just typing Y in the dialog box, you can launch download, which went quite fast in this example. So you can see that the file has been successfully downloaded. Here is the name, so there is a 1 here because I had already downloaded it, so it's just a duplicate. And we can see here that it is here in my data directory, so the download was successful. So as I said, all the data products are already provided in this training, but you can try to download them using only this toolbox. So here is the example. So we just downloaded it, and using X-array we can, as a test, open it, and you can see that we have our product with the sea surface temperature here. You can, by clicking here, get more information about the data. Here we have our time variable. We can see that it goes indeed from the beginning of February 2020 to well, right before April 2020. So this is what we specified, and our latitude and longitude are also consistent with what we had specified. So now we're going to study our case study, so the Congo river discharge. So first of all, we're using Python, and we're using the a few libraries that are installed in the CMEMS kernel. So if you're already familiar with Python, you are probably familiar with those libraries already. So we're using NumPy, that is quite essential for scientific computing in Python, especially when managing data arrays. Xarray in Python is widely used to open netcdf products, which is what we are using. So that's why we're using the Xarray library. And finally, matplotlib and cartopy are used to plot visuals. So cartopy is dedicated to maps, and matplotlib is dedicated mainly to plots and figures. So in this cell, we are going to import all these libraries. And now, in the next cell, we're going to load all our products. So here you can see the path to the physical model, biological model, and the observation products. So here is the sea surface temperature, SST, and here is the observation product for chlorophyll. So here is the example of the Xarray, of the product opened with Xarray. So here is the biological model. We can see that we have a lot of different parameters, and in our case, we're going to be interested in the chlorophyll products here. Its mass concentration in water. So you will see that that's what we're going to observe. So in this section, we're going to observe the river discharge across time, and we're going to do that through an animation. So here in this cell, we are going to actually create a series of images. Here, as you can see, we're going to create one image per time step. And so I'm going to start executing the cell now because it takes quite a little time to execute. So I'm going to talk as it executes. So to give you a brief summary of what those lines do, they are all dedicated to drawing the map of the river discharge near the mouth of the Congo River. So this line just create the window for the map. With this line, we just choose the map projection that we want. So we just want to use flat 2D maps, but there are more sophisticated projections that exist. Here we just activate the longitude and latitude grids. Here we draw the coastlines of the continents. Here we just deactivate the labels in order for better readability and for also aesthetics. Here we had the feature that is the land in order to have a color differentiation between land and ocean. And finally, we zoom on our area of interest, setting the extent here and specifying our longitude, minimum and maximum longitude and latitudes. And here we just set the title, and with this function pcolor, we color the map according to the variable that we have chosen. So here you can see that we are plotting salinity. This is this variable from the physical model. And finally, those last lines are used to draw the color bar to legend the map. Here we save the figure in the out directory. And here we just do that because here we just producing images to be saved in the directory to build an animation later, but we don't want to display them all of them all at once on the screen. So this is why we do this to deactivate the instant display in the notebook, because there would be dozens of images and we don't want that, it would be unreadable. So we're going to wait, it is still executing. I'm going to go back to you in a few seconds when it's finished. Okay, so you can see that now it's not a star, it's well, the number of cells executed that is displayed. So this means the execution is finished. So we can keep on. So in this section, we're just going to display the animation that we have built. So as you can see, all our images are in the out directory. And now we want to gather all of them and make a GIF images. So we're using the libraries that are used to make the animation. Here we gather all the images, so you can see that all the images that are called sal date with any extension are going to be put together, and the output will be this animated GIF. And now with this cell we display it. And now here in this animation we clearly see that around the rim of the mouth there is a much lower salinity than in the open ocean here. And you can see its evolution through time. So here we are in February, in March. So we can see that this the salinity pattern varies over time, probably due to river flow and ocean currents. So now we're going to continue this study by looking at the sea surface temperature and chlorophyll and compare the model versus the observations. So once again, we're going to compute animations for all these products, so observation and model, and chlorophyll and sea surface temperature. So this is what we're doing with this cell, also drawing maps, but this time we're going to draw 5 maps at once with for each of the 5 one map per time step here. So once again, this cell is going to take quite a few seconds to execute. So I'm just going to pause the recording and get back to you as soon as it's finished. Okay, so it took a few minutes, but it's finally finished executing. So don't worry if it takes. So if you think it takes too long, it does take quite a few minutes. So all our images are saved. And now we're going, just like before, to load them all in an animation. And here you can see that we have all the animations here. So we have our salinity that we have already calculated before. And here are the temperatures and chlorophyll observation versus model. And we can see many things in this plot. So first of all, we have what we have already observed, that the river discharge decreases the salinity around the river mouth. Here, on the contrary, the river discharge does not seem to globally affect the ocean that much. And here we can see that for chlorophyll, the reverse discharge of nutrients tends to increase the amount of chlorophyll in this region. But also it appears that the model seems to underestimate the amount of chlorophyll that is actually observed at the river mouth. So if you want to go further, I have an exercises to propose to you. So as you can see here, we've only looked at chlorophyll, for instance, but as I've shown you in the model products, you have many variables available. So here in the biological product, you do have chlorophyll, but you also have many other variables. For example, here is the phosphate. So it's one example of a typical nutrients that can be carried out from the land to the ocean by the river. Same with nitrate, for example. So you can totally perform the same analysis only using those variables instead of chlorophyll and see what your results are. So this could be quite interesting, and I encourage you to try this. So finally, we are going to sorry, this is not the final section. So we're going to see how the river discharge affects the ocean on the more global scale, still remaining at the surface of the ocean. We'll study the deeper ocean later on. So to do this, we are going to define three areas of interest around the river mouth of Congo River. So they are defined here in this cell with the coordinates. And here we are going to visualize them in order to have an idea of what we'll be looking at. So here you can see that we have our three areas of interest. So first of all, we'll be only considering one single point located directly at the river mouth. On the second time, in this way, yes. Secondly, we're going to look at what's at the data located within this little square here. So we're going to look at well, all of the closed area around the river mouth, and we're going to study the region on a larger scale. So you can see that we have more parts of the open ocean located within our area of interest. And so for all areas, we're going to look at the time series of the and perform the spatial mean. In order to see if from area to area the different variables are correlated or not. So here in those cells we perform the spatial means of the product to keep only the time series across the areas of interest. And we can see how those measurements or well, model outputs vary over time. So here we're considering the models, salinity, temperature, and chlorophyll. And we can see that for each of them, the point and small area of interest are often quite correlated. Except here for salinity, we observe some sort of bump here. But the correlation for salinity seems less obvious when considering the bigger area of interest. On the contrary, for temperature, all three areas of interest are very correlated. So this indicates a much smaller influence of the river discharge on the temperature of the global ocean. And this is for chlorophyll, that the difference between the closed area around the river mouth, whether it's only the point or the small region, and the bigger region are the most different. So this suggests that the river discharge has only a very local impact on the chlorophyll concentration. Now we will do the same thing, but for the observation products. And here we can see that the strong correlations that we had before are not necessarily as strong here. We have a similar phenomenon of this salinity bump here for the salinity. But for temperature, for instance, especially between the point and the smaller region, we can see that we have quite a gap here, for instance. And the most obvious is for chlorophyll, where we have strong spikes here that are not found within the big region. So we have correlation that well, observable, but maybe not as obvious as with the model product. But still, we can see that even in the observation, for salinity and especially chlorophyll, the impacts of reverse discharge are much more local, are strongly local, on the contrary to the temperature. And so, as an exercise, I propose to you that you reproduce those analyses, but not necessarily on the Congo river mouth, but I encourage you to find a different location and perform the same analysis, just changing those coordinates, and see what your results are. You can try another river mouth, the Nile or the Seine or the Loire. It's up to you. So finally, we are going to observe the effect of the reverse discharge on the deeper ocean. So, and to do that, we are going to plot new graphs, which are called Hove model diagrams. So it's basically the evolution of the vertical profile over time. So on our plots, the x-axis will be time, and the y-axis will be depth. So this is what we plot with this cell, and we have our three products, which are all coming from the model. Because of course, with satellite products, you only get data from the surface. So as we can see here, we have what seems to be an inverse correlation between salinity and temperature. You can see that on each vertical profile, when the salinity is quite strong, the temperature is on the contrary quite low, and contrary here. And with the chlorophyll, we have a different pattern. So we can see that when the salinity is low, which means when the river discharge is strong and the input of fresh water is strong, and well, we also have nutrients that lead to quite high concentration of chlorophyll on the surface, and this chlorophyll concentration is weaker when the salinity is strong, which accounts for well, a weaker river discharge. So we're reaching the end of this training. So I encourage you to do the exercises that I've mentioned. Now you have plenty of tools to manipulate ocean products with Python, and also you've learned how to access data using the new Copernicus Marine Service toolbox. So thank you for following this training course. I hope you enjoyed it, and I hope you well, have fun using these products. Thank you very much, and goodbye.